Welcome back to the course on symmetry, stereochemistry and applications. In this course, we have already discussed about the nomenclature of organic compounds, and after that, we started discussing about the stereochemistry of simple organic molecules. And in the previous lecture, we had understood the different conformations of cyclohexane and monosubstituted cyclohexane derivatives. So, in this lecture today, we will try to understand the conformations and conformational aspects related to disubstituted cyclohexane molecules. So, in that, we would like to start with the cis-1,2-dimethyl cyclohexane. So, when we write cis-1,2-dimethyl cyclohexane, as you may be writing from your previous knowledge, we used to write cyclohexane as a hexagon, and when you say cis, that means you have two methyl groups on adjacent carbon atom with both of them upwards and with the corresponding hydrogens downwards. So when we try to draw this molecule in the chair form, we should remember that both the methyl groups should remain in the upward direction. So if we try to draw the cyclohexane in chair form, we should draw this 1,2-dimethyl in this fashion. So this methyl group here should be up, and the other methyl group on that carbon also should be up. And here the hydrogen is down, and there the hydrogen is down. So this is the conformation of cis-1,2-dimethyl cyclohexane. So here this methyl group is axial and this one is equatorial. This methyl is in the equatorial position. This methyl is in the equatorial position. So, if we try to flip this molecule, what should happen? On flipping, this molecule should flip like that. So this methyl group, which is up here, should come down. The hydrogen associated should be up. The methyl there should be down, and the hydrogen there should be up. So this makes it same in terms of the conformation, because if we try to draw the Newman projection of these particular two conformations looking at this CC bond and through that CC bond, and here through this CC bond and that CC bond, what do we see? So here what we are trying to draw is the Newman projection of this cyclohexane conformer. So on the first carbon here, I have a methyl group in the equatorial position. This hydrogen is in the axial position. Then it connects to this carbon. Suppose if I number it as 1, 2, 3, 4, 5 and 6. So it connects to the carbon 3 here like that. And then on carbon 3 we have one hydrogen here and the other hydrogen there. So then on carbon 4, this axial hydrogen is here, that equatorial hydrogen is here, and the bond from 4 through 5 to 6 is like this. So this is your carbon number 2, 3, 4, 5, and the back carbon is 6 with this as 1. So then you have a methyl group which is present there, and the hydrogen which is present here. On flipping, what do we get? On the front carbon, the methyl is down, the hydrogen is up, and it connects to the other carbon like that. So through, if this is 1 and that is 2, this is 3, it connects to 3, and 3 has 2 hydrogens, 1 axial and 1 equatorial, and then the atom 4 will have hydrogens here, there, and it connects through the carbon number 5 to the back carbon 6 like this, and the back carbon has methyl downwards and this hydrogen upwards. So now if we try to remember our understanding with butane, we had the N-butane Gauss interaction due to the presence of 2 methyl groups in the Gauss position at the 60-degree interaction. So that interaction is present in both the conformations. Therefore, these two conformers are equally stable at room temperature or any temperature, and there is no preferential stabilization of the other one or the other, because in both the cases you have one methyl group in the axial position and one methyl group in the equatorial position. So cis 1,2-dimethyl cyclohexane has only one conformation that we can find from here. Now if we move to the trans isomer of 1,2-dimethyl cyclohexane, let us draw it once again as a planar molecule, as we are very familiar to draw. So we write one methyl up and the other methyl down, with the hydrogen here up and hydrogen there down. So now if we try to draw this trans 1,2-dimethyl cyclohexane in the chair form, it would look like this. Hydrogen down, methyl up, here methyl down, and hydrogen up. So this is trans 1,2-dimethyl cyclohexane, where one methyl here it is equatorial, this methyl is also in the equatorial position. When we flip, what happens? On flipping, the methyl here would go up, the methyl hydrogen there will come down, this hydrogen will go up, and this methyl will come down. So it becomes diaxial from di-equatorial. So let us now try to draw the Newman projection of these two, looking at those bonds as we had done in the previous case, and we try to number those atoms as usual. So on the first front carbon 1, we have a methyl group here, one hydrogen down, and this connects through 2 to 3 like that, 3 has one hydrogen down, one hydrogen here. The carbon 4 has one hydrogen in the axial position up and the equatorial down. You should remember that H axial is here, and the corresponding connectivity from 4 to 6 is through 5, like that. And in that, the methyl is down and the hydrogen is up. And then if you try to flip, what we would get on the front carbon, the methyl is down, the hydrogen is up. It connects through the carbon number 2 to 3 like this, and this hydrogen is axial, which is here. This hydrogen is the equatorial hydrogen, which is upward. Then the next hydrogen here is axial, this is equatorial, and then you join these two bonds, and then look at the back carbon, which has methyl there and hydrogen here. So what we see now is, in this conformation, again the two methyl groups are at 60 degree, which is equivalent to that N-butane Gauss interaction, while that two methyl groups are anti here, but they are now in diaxial orientation. So what will happen is, if you see this conformer here in the diaxial conformation, you have the hydrogens which are up. There will be diaxial interaction with the methyl and hydrogen groups, 1,3 diaxial interactions. So in that case, here also there will be diaxial interactions in the methyl groups. So then one has to compare the energy values associated with the N-butane Gauss interaction and the corresponding 1,3 diaxial strains and decide which molecule, which conformation is more stable than the other. So this I would like to leave it to you to find out among these two which is going to be the more stable conformation. Now let us see the situation with 1,3. Till now we have discussed about the 1,2 disubstituted, which means two adjacent carbons have the substitution. Here it is 1,3, which means there is a carbon gap between the two groups which are on two carbon atoms of cyclohexane. So if we draw it like that, we can understand easily that these two methyl groups are both upwards, but on 1 and 3 carbon atoms. So if we try to draw the chair conformation of this molecule, and we take this carbon as carbon number 1, so then this methyl which is up should have a hydrogen down. Second carbon does not have any methyl group, so 2 hydrogens, and third methyl group, third carbon atom has 1 hydrogen down and the methyl group in the equatorial position but up. So what we see here is that the two methyl groups that we have are both in the equatorial position. So now when we try to flip the chair, what would happen is that the methyl group on this carbon will come down to the axial position. The hydrogen will be in the equatorial position. This does not have any methyl group. This has 2 hydrogens. The third carbon, which is here, is a methyl group down, and the hydrogen in the equatorial position. Here is hydrogen axial, equatorial, and again axial and equatorial. So what we see here is the two methyl groups both are in the axial position on 1,3 dimethyl cyclohexane. So what we now have is a very strong 1,3 interaction between the methyl groups and the hydrogens, and it is very obvious that this 1,3 diaxial two methyl groups 1,3 dimethyl cyclohexane in the cis conformation, cis isomer, you have a very strong 1,3 diaxial interaction. So if we try to draw this molecule using the Newman projection as we were doing in the same way like before, on the front carbon here we have a methyl group in the axial equatorial position. There is one hydrogen. These two are connected through 2, and then you have the hydrogen here, hydrogen in the equatorial position. Then on the carbon 4, this is the equatorial hydrogen, and on the carbon 4, this is the axial hydrogen. This methyl is connected through 5 to that, this, and that are the corresponding axial and equatorial hydrogens. The methyl group here is in the equatorial position, so the hydrogen is here and the methyl group is in the back side. This is equatorial, don't mix it up. So what we see here is this methyl and that methyl are far apart, so there is no question of N-butane Gauss type of interaction, and this conformation does not have 1,3 diaxial strain, so therefore this conformation is always more stable compared to the other conformation. Let us try to draw the other conformer in the Newman projection for our understanding. So on the front carbon we have a methyl down, hydrogen. This connects to 3 like that. That has a methyl down, hydrogen up, and then this and that connects through carbon number 5, which is in turn connected like that. And in this 5, we have a methyl group downwards and the hydrogen upwards in the backside direction. So it is very clearly seen here that these groups are very close and they interact through 1,3 diaxial interactions, and hence this is less stable. So always at room temperature, this 1,3 dimethyl cyclohexane in the cis form will stabilize in this chair conformation compared to the other one. Now let us see what happens when it is trans 1,3 dimethyl cyclohexane. So as usual, if we draw it as a planar cyclohexane ring, which we are very familiar to draw, if one methyl is down, the other methyl is up, is the representation of trans 1,3 dimethyl cyclohexane. So when we try to draw the chair form of this 1,3 dimethyl cyclohexane, very efficiently we should start drawing the methyl groups first up. Second carbon does not have any methyl group, so 2 hydrogens. Third carbon has a methyl group, but if this methyl is up, the other methyl is supposed to be down, so the methyl is here and that hydrogen is there. So it is very clear that if this is in the equatorial position, that is in the axial position in the third carbon atom. Now if we try to flip this, what should happen? In the flipped condition, the axial bonds will become equatorial bonds and equatorial bonds will become axial bonds. So the methyl group which was here would be down and the hydrogen will be up. So it will become axial. The second carbon does not have any hydrogen, so it is up and down. The third carbon which had a methyl group in the axial position, the hydrogen will be in axial now and methyl will be equatorial like that. So what happens is now here we have a situation where one is axial and other one is equatorial, and on flipping the equatorial becomes axial and axial becomes equatorial, which means both the conformations are of same energy and they coexist in the equilibrium. So I would leave this for you to draw the Newman projection and understand yourself how that is possible. So now we will move to the next molecule, which is 1,4-disubstituted cyclohexane, that is cis 1,4-dimethyl cyclohexane. So when we draw that cis, two methyl groups are up and two hydrogens are down on 1,4 position. So if we draw the corresponding molecule here in the chair conformation, this, by making this methyl up and the hydrogen down, and on the fourth carbon making the methyl up and the hydrogen on the down, this is cis 1,4-dimethyl cyclohexane. So remember that now here it is equatorial and the other one is axial. If you flip, it goes like that. On flipping, this carbon has the methyl up, the hydrogen down, and the carbon 4 has hydrogen in the down and methyl in the up position. See here, this is axial and this is equatorial. Once again, these two conformations have one methyl in the axial and one in the equatorial position, and in either conformation the condition does not change. So these two conformations again have the same energy. So if we try to now draw the Newman projection of one of those, we will be able to understand what are the interactions that are present here. So we number those atoms as usual and draw these groups as we have already done. So I will quickly draw this Newman projection for you. So we have 1, 2, 3, this is the fourth carbon, and on fourth carbon I have the methyl group in the axial position, and here I have the hydrogen. This connects like that and this. So here what we have is, as usual, the methyl-methyl 1,3 diaxial interaction 2 times. Similarly on that one, this hydrogen and that hydrogen, these two are up. So we will again have the 1,3 diaxial interaction present in that, and that is why these two conformers are of same energy. Now let us see what happens when it is the case of trans. So in case of trans 1,4-dimethyl cyclohexane, if one methyl group is up, the other methyl group is down. So if we try to draw it here, this methyl group, if we draw up, the other methyl group we should draw as down. So now if we see here that this is axial and that is also axial, which means for that particular methyl group, there will be 1,3 diaxial interactions with these axial hydrogens. For the other methyl group, there will be 1,3 diaxial interactions with the other two hydrogens. So it will have twofold effect of 1,3 diaxial interactions with two methyl groups. If we now flip the molecule, what we would have, if we flip the molecule, we would have this methyl group in the equatorial position, and that methyl group once again comes to the equatorial position, and that way we avoid the 1,3 diaxial interactions. Therefore, this conformation is more stable than the first conformation that we have drawn. So if you try to draw the Newman projection of the first conformation, it should look like this. You see here on the back carbon you have a methyl group. The hydrogen is here, the back carbon is connected to the back carbon here, and the hydrogens on that are these. And the methyl group that we have on this front carbon is downwards, hydrogen, methyl, hydrogen and hydrogen. So what we have here is very easily seen that this methyl hydrogen 1,3 diaxial interaction is present on either side of the molecule and giving it a less stability. But when you try to flip the molecule, then you will see that these two groups have methyl groups in the equatorial position and the 1,3 diaxial strain is avoided. So in this lecture, we have understood the conformation of disubstituted cyclohexane derivatives, and we have understood how to draw those in this chair form and how to convert those chair form conformations to the Newman projections and calculate the interaction energies based on whatever interactions are present. So I would like you to go through the textbook for this part, get the energy values for 1,3 diaxial interactions and the N-butane Gauss interactions and calculate yourself to find out the energy values associated with these conformational differences. So with this, we would like to conclude this lecture and we will continue from here. Thank you.